tiny integrated circuit, so small that the wires that connect it are 1/4 the size of a human hair, encased in a protective plastic shell. The same development that brought us out of the bulky mechanical age and into an era of efficient microcomputer technology has made its way into one of the most brutal of industries. For years, the hydraulic closing systems on offshore drilling rigs have been connected to the BOPs by bulky, multi-hosed hydraulic bundles. For shallower water depths of up to 1,500 feet, these hydraulic signals were used to pilot the subsea valves of the BOP stack on the ocean floor. However, as drilling depths increased, these hydraulic control systems became cumbersome, and the response time of the controls at these increased depths was not as fast as we would like them to be. So the multiplex BOP control system was developed. Unlike the old hydraulic system's response time, the multiplex system is almost immediate because the electronic signal sent from the multiplex brain travels at a much faster speed than the hydraulic signal. The cable that links the electronic controls to the subsea system is a relatively small diameter armored composite cable containing 21 conductors. This cable is hooked up to an electrical connector that we call the Multiplex 21 or MUX 21. This series of training tapes will center around the design and use of this cable and connector. It will also deal with another cable, the fluid-filled pressure-compensated jumper cable, or as we call them, the FFPC cable assemblies. First, we'll examine the design of the Multiplex 21 cable and connector. It's about 7,000 feet long. Inside, there are 21 separate leads that are grouped together in 7 different composites and 3 combinations of cabling assemblies. First, there are 2 large number 10 AWG power cables that supply 480-volt AC power to the subsea control system. Second, there are 2 identical coaxial cables that are used to carry the television signals from the stack-mounted television cameras to the surface. Last, there are 3 twisted shield quads consisting of 4 small 20-gauge conductors twisted together and surrounded by a shield. Each of these 7 composites is covered with a polyethylene plastic jacket. The 7 assemblies are bundled together and bound by 2 layers of plastic tape. The cable manufacturer then covers this entire assembly with a polyurethane sheath approximately 1/8 of an inch thick. This plastic coating, plus the plastic coating around the individual composites, ensures that the cable will be watertight from end to end. The plastic coating is strong, but not strong enough to support the weight of the entire cable. Also, since the cable is attached by a special clamp device to the marine riser while it's being run through the rotary table and the moon pool, it must be protected against possible mechanical damage. So steel strands are spun around the plastic, first counterclockwise. Then, to give it additional strength and to keep the weight of the cable from twisting in the direction of the steel wrap, a second layer is spun around the cable, this time in a clockwise direction. As the steel armored strands are wrapped, the completed cable is spooled onto a large storage reel. The next step is to attach the connector to the cable. We call it the CCP, or Cable Connector Plug. For some, it may be easier to think of this as simply the plug, since the CCP is very much like the plug on the end of the lamp cord in your home. Just as the lamp cord plugs into the receptacle in the wall, the multiplex cable CCP plugs into its receptacle. The receptacle is called the FCR, or Flange Connector Receptacle. We'll talk more about the FCR later. The procedure for terminating the CCP is complicated because this connector was designed to withstand at least 3,000 pounds per square inch of pressure without any connector leakage or internal leakage into the cable itself. Sedco's engineering department in Dallas worked very closely with the Vector Cable Company of Houston to design a special connector system that would ensure the most reliable BOP control system available. The first step in attaching or terminating the CCP to the cable is the termination of the armor covering of the cable to the tail end of the CCP. A good, solid connection is necessary, so each armor strand is separated. Cut to the proper length and bent like a fish hook. Then a strong epoxy resin is poured into the area in back of the connector around the armor hooks. This section of the connector is called the armor termination pot, or armor pot for short. A rubber boot is put on the cable and connector to help reduce the strain on the wires inside the cable where it enters the connector. It's called the stress relief boot. You should be aware that on some of the first cables, this boot was molded around the cable armor by the manufacturer. Since then, Vector has developed a field replaceable boot that can be installed on board the rig without the need of a mold or press. Below the armor pot, the cable, surrounded by its plastic jacket, enters the sealed cavity of the CCP through the jacket seal plate. A rubber boot fits tightly over the plastic waterproof covering and seals over the neck of the jacket seal plate. There are two sets of double O-ring seals between the jacket seal plate and armor pot, and at the armor pot and service sleeve. They create a leak-proof area between the inside of the armor pot and the cavity area of the service sleeve. The armor pot and the service sleeve are then bolted together. Beyond the jacket seal plate, the outer plastic covering is removed. And the 7 composite lead bundles are separated. Another boot seals the 7 separate lead bundles to the jacket seal plate on the inside of the cavity area. This gives us both an outside and an inside seal where the cable enters the connector cavity. The 2 power cables are terminated directly to their respective contacts and sealed off with yet another boot. The multiple lead bundles are separated out and each lead is fitted through a multi-legged boot before they are terminated and sealed to their respective contacts. As you can see, each wire is thoroughly sealed from its contact through the multi-legged boot of the composite, and then each composite is individually sealed at the jacket seal plate, and the jacket seal plate is sealed to the outer jacket of the cable. We have a name for this: single wire integrity. Single wire integrity means that if for any reason should one conductor be flooded with salt water, the water cannot migrate into another conductor of the cable. This single wire integrity concept is carried through even to the contacts on the back of the CCP head plate. Each conductor goes to its own separate contact, and each contact is replaceable. Each receptacle has a double seal that seals against the head plate to prevent leaking, and the head plate is sealed to the assembly sleeve with a double seal. As we've just shown, the cavity of the CCP is totally sealed off from the outside subsea pressures by double O-ring seals at the sealing surfaces of every fitted section. This is the first unique feature of the connector. The second is its pressure compensating design. When the CCP is assembled and the riser package is on the ocean floor under 6,000 feet of water, the hydrostatic pressure exerted by the seawater is approximately 2,800 pounds per square inch. To keep this pressure from crushing the outer sleeve of the CCP, the cavity is filled with a special oil called DC-200. DC-200 is electrically non-conductive, and it doesn't compress easily under extreme pressure. But most important, DC-200 is compatible chemically with all the rubber elements inside the connector. Remember that DC-200 was chosen specifically for the compensating fluid in the multiplex connector. You should never use any type of transformer oil or hydraulic oil in the MUX-21. These rubber bladder devices are called Greer accumulator bags. The bags extend into the CCP cavity. The inside of the bag is connected through a port to the vented armor pot to allow the sea pressure to act inside the bags. As the connector is lowered into the water and pressure increases, it causes the accumulators to expand, which transmits the pressure to the DC-200. The DC-200 then becomes pressurized due to the expansion of these bags and pushes outward on the sleeve assembly of the CCP with a pressure equal to that of the seawater pressing from the outside. So this is how the compensation system keeps the CCP from being crushed by extreme subsea pressures. As you can see, the MUX-21 CCP is designed for the worst operating environment we can imagine, plus a reasonable margin of safety. It's virtually impossible that the CCP will develop a leak due to design failures. But no matter how carefully this connector system is designed, the ultimate reliability depends on you. On board the drilling rig, the top end of the cable is attached to either the blue or yellow multiplex cable reel. At the other end of the 7,000-foot cable, the CCP is plugged into its receptacle, called an FCR, or flange connector receptacle. When the CCP and the FCR are connected together, there are sufficient seals throughout the FCR to ensure against leaks. First, there are 3 O-rings that seal between the junction box and the receptacle. There are even O-ring seals between the pins on the receptacle and the individual female inserts on the plug. Yet one of the most important aspects of the FCR design is the number of test ports to allow testing of the connector after it has been mated. This is the third unique feature of the connector. If an O-ring were cut, or if a seal surface were scratched, it could easily be detected during the pressure test before the BOP is run. Even with all these special design features, the Multiplex 21 is still vulnerable to damage. Although the cables are armored and the connector is made of heavy stainless steel, they're really very fragile. Careless handling of the connectors will lead to eventual failure. You know what we mean, banging them around and not installing the protective devices when not in use. Yes, there are protective plates that have been provided to be put on the end of the CCP, and a protective cap is also furnished to cover the FCR whenever the two aren't mated. These are used to keep foreign matter out of the FCR and to prevent damage to the pins or the contact receptacles. Just be sure that the protective cap is clean before installing it. But most important, be sure that you use it. You should also be careful with the armor cable. Inside the strong doubled armor shield, there are some pretty small wires, the kind that you can snap apart with your hands. That's one of the reasons for all that double armor protection, to keep the cable from bending at too sharp of an angle and causing the small wires to snap. Another problem that has occurred more than once is particularly important to the welder. The armor shield on the cable is grounded to the rig, so when you're welding around the cable, be careful not to touch it with your welding rod. That can sure make life rough for you. Well, that's a pretty good introduction to the MUX 21 design features. The double armored cable contains 21 leads that are individually bundled as 2 single power leads, 2 coaxial leads, and 3 shielded quads. Each lead is sealed by a series of boots, and the armor is anchored to the connector by a strong epoxy resin. All assemblies are double sealed by O-rings and cable boots. The 2 Greer accumulator bags provide internal pressure compensation against the DC-200 non-conductive fluid to counteract the excessive external seawater pressure. Well, that covers the vital link between the rig and subsea controls. But what happens after the signal reaches the ocean bottom? The subsea multiplex unit decodes the computer-like words it receives from the surface. The decoded words switch a direct current, or DC signal, to the solenoids in the electrohydraulic pod. These solenoids control the pilot pressure to the subsea valves that control the BOP functions. In order to get the electrical signals from the subsea multiplex unit to the electrohydraulic pod, SEDCO and Vector engineers have developed underwater electrical jumper cables. In fact, these jumper cables are used as the interconnecting cables to link the different parts of the subsea multiplex system, including the electrohydraulic pods, the underwater television system, and the riser angle indicator. The same pressure compensation designs and features were needed in this jumper cable as were required in the MUX 21. Since the cable length was limited, the great strength designed into the multiplex cable wasn't necessary, so a different configuration was developed. In order to make the jumper cables entirely field repairable, no molding was allowed, and all seals had to be done by mechanical boot seals. Also, the individual wires were pulled through an outer conduit so that in the event of the failure of one wire, it could be removed without disturbing the others. Because this outer conduit is subject to the extreme pressures of the ocean floor, it needed to be pressure compensated. The simplest approach was to make the conduit out of a rubber hose material and to fill that hose with a compensating fluid like DC-200. That's exactly what was done. The result is a fluid-filled, pressure-compensated FFPC cable assembly. The FFPC cable is made up of a length of rubber hose about 1/8 inch thick, a connector at each end, and a set of individual leads that run through the hose from one connector to another. The hose is fitted over the neck of the FFPC plug, or CCP, and secured by stainless steel hose clamps. Inside the CCP, a wafer with holes positions the leads exactly the way they'll be terminated onto the insert. The insert is a single molded plastic piece with female receptacles. The receptacles are not removable, so if one is damaged, the entire insert must be replaced. The edge has grooves where O-ring seals fit. When the insert is installed in the CCP and the snap ring is in place, a good tight seal is effected. The backside of the CCP and the hose cavity are filled with DC-200 through this port. As with the Multiplex 21 CCP, the DC-200 acts as the compensating fluid in controlling the excessive subsea pressure. The rubber hose acts the same way that the Greer accumulator bags do in equalizing the pressure. The more pressure that is exerted on the hose, the harder the DC-200 pushes on the connectors, equalizing the pressure. There is one additional feature designed into the FFPC series connectors. When the CCP and the FCR are mated together, normally there would be an air gap between the two inserts. Since there are seals sealing the external atmosphere out, this air bubble would create a compressible pocket, and the receptacle lock ring would snap under the excessive pressure. But this little valve has been designed into the CCP insert. When the two connectors are mated, the valve is opened, allowing the DC-200 fluid to flow from behind the CCP into the air gap. The fluid then fills the void of the air gap and prevents the CCP insert from snapping the lock ring out of position. So as you can see, the FFPC uses its flexible outer covering and the DC-200 inside as a pressure compensating system. This single-piece molded insert contains a valve to pressure compensate the air gap between the CCP and the FCR when the connectors are assembled. The FFPC series connectors, like the Multiplex 21 connector, can also be hydraulically pressure tested after mating before running the BOP stack to bottom. We'll cover this operation in a later program. The entire system, although complicated, is one of the most reliable devised to date and should require only moderate attention. For each element, from the valves to the control pods to the FFPC cable to the Multiplex 21 connector and cable, and finally to the surface controls where the tiny integrated circuit feeds the signal, there is no finer system available. Yet the communications link has always been the single biggest problem in an electrohydraulic control system in the past. This communication link remains vital to the successful operation of the BOP controls. And now the most vulnerable part of the system is in your hands.